We're now going to look at the method by which we can calculate the empirical and the molecular formulas for compounds. And let's just quickly review what an empirical formula is. It's the simplest whole number ratio of the substances present in the compounds. All ionic compound formulas are empirical formulas. Molecular formulas can be both empirical formulas as well as molecular formulas in the case of water, or in benzene, they can be different. Let's take a look at this table. Benzene is an organic substance with the formula C6H6. Now, as soon as I look at that molecular formula C6H6, these are the actual numbers of carbon and hydrogen atoms present in the bonding structure that makes up the molecule. But I immediately see that C6H6 is not the simplest whole number ratio for benzene. We can divide the subscripts through and come up with an empirical formula for benzene of CH. So in benzene's situation, its empirical formula, which is not its actual structural composition, but just the simplest whole number ratio, is different than its molecular formula. In the case of water, H2O, that's its actual chemical formula. 2 hydrogens bonded to 1 oxygen. I see that the molecular formula can't be reduced down any further, so water's molecular formula and its empirical formula are both the same. Sodium chloride, table salt, is not a molecular compound. It's an ionic compound. So the concept of molecular formula does not apply to it, and I leave it blank. All ionic compound formulas are empirical formulas. So remember, we discussed that sodium chloride is this huge 3-dimensional array. And in a previous illustration, when we were talking about ionic bonding, I showed you the crystal structure of sodium chloride as a huge array, and the ratio of sodium ions to chloride ions is 1-to-1 in the compound. So all ionic compound formulas are empirical formulas. Notice that we can determine the relationship between the empirical formula and the molecular formula of a compound using the concept of N. N is always a whole number, simple whole number, 1, 2, 3, 4, and so on, that you multiply the subscripts of the empirical formula through by to get the molecular formula. So in the case of benzene, N would be 6. In other words, we would have to take the empirical formula of benzene and multiply it through by 6 to get the molecular formula of benzene, C6H6. In the case of water, N is 1. And the empirical formula, multiplying all those subscripts through by 1, gives you the exact same molecular formula. So for water, N is 1. And of course for sodium chloride, N is not applicable because you don't have a molecular formula for an ionic compound. They're all empirical formulas. Let's take a look at this flow chart for calculating an empirical formula. And you can find this flow chart on page 188 of the text, where in section 6.8, where empirical and molecular formulas are discussed. So here is a flow chart for calculating an empirical formula. You either need to have percent composition data. What is the percent by mass of each element in the compound? So you either have to have the percent composition data, or you have to be told what the experimentally determined masses of each element are in a sample of the compound. So I'm going to put the word start, meaning you can start from percent composition data, or you can start from the actual masses of each element in the compound to calculate an empirical formula. If you start with the percent composition, then you simply assume that you have 100 grams of the compound, and the mass percent then becomes the actual grams of each element. And I'm going to illustrate this idea in the sample problem we're going to do next. So starting with a percent composition, assuming 100 grams of the compound gives you automatically the grams of each element in the compound. Once you have the grams of each element in the compound, you're going to use the molar mass or the atomic mass of the element and convert to moles of each element in the compound, because chemical formulas give us mole ratios of the elements in the compound. Once you have moles of each element, you need a whole number ratio of the elements in the compound. So you're going to divide through by the smallest mole amount to get the simplest whole number ratio. And to illustrate that last part here with the example of water, if I told you that you were looking at a situation where you had a formula H3O1.5 and say, what is that? You'd go, well, I don't know what that is, because formulas are always in simplest whole number ratios. But if you take a look at these numbers and divide both through by the smaller mole amount, you come up with H2O. And all of a sudden you go, oh, I know what that is. That's water. So that's what we're talking about here in the very last step, taking the moles of each element, which are not written in the form of whole numbers most likely, and dividing through by the smallest mole amount to come up with whole number mole ratios. And let's go ahead and see how we can illustrate this process using the compound benzoyl acetate. Benzoyl acetate is an organic compound, and it has a lovely fragrance associated with it. It is commonly known as oil of jasmine, a lovely fragrance for me to smell. So chemical name benzoyl acetate, but known as oil of jasmine. And you are being asked to calculate, and we're going to do this together as an example, the empirical formula and the molecular formula of benzoyl acetate. And notice what I've given you for data to do the problem. In order to do the calculation, you either have to have the percent composition or the mass of each element in the compound. And I have given the percent composition of benzoyl acetate, so we're starting the problem right here using percent composition data. What are we going to do? We're going to assume 100 grams, and each of these mass percents becomes the actual grams of each element present. In other words, if we had 100 grams of benzoyl acetate, we'd have to have 71.98 grams of carbon present. So notice how I've set this problem up. I've lined up the elements that are present in the compound, carbon, hydrogen, oxygen, vertically. I've taken their mass percents and dropped off the percent and put a gram unit with it, assuming that I have 100 grams of the compound. So I'm now right here with a mass of each element. Now I want to use the atomic mass or molar mass of each element and find how many moles of carbon and hydrogen and oxygen I have. So I started the problem out, but let's do this calculation together, right? Taking our calculators and taking 71.98 and dividing by 12.01, I come up with 5.993. 5.993 moles of carbon. Since there's so many numbers that we need to use in this calculation, it's always a good idea to double check that we did that calculation right, and I'm getting the same answer a second time. Now I'm doing the same calculation for hydrogen, taking the mass of hydrogen, converting to moles, using the molar mass of hydrogen, and I am going to get a number here of 6.64 moles of hydrogen. Making sure I'm careful with my sig figs and not dropping off sig figs in the problem. For example, if you write the answer for this calculation with only 2 sig figs instead of 3, that error, which is in essence a rounding error, can throw off the ratio of atoms in the formula. So it is very important that you pay attention to the correct number of sig figs when you do the calculation. And double checking my answer again, I come up with the same moles of hydrogen, 6.64. And now lastly, I'm going to take the 21.3 grams of oxygen and find how many moles of oxygen I have by dividing by the molar mass of oxygen, which is 16.0. And when I do that calculation, I get 1.332 moles of oxygen. So here are mole ratios of carbon, hydrogen, and oxygen in benzyl acetate. But we know that we never write formulas using fractional amounts. So we cannot write this formula like this. What is that? We don't recognize it. Instead, we have to come up with the simplest whole number ratio, which is what an empirical formula is. And how are we going to do that? We're going to take a look at these mole numbers and divide them all through by the smallest mole amount. So as I inspect these 3 mole values, I see that oxygen's mole amount is the smallest. So I am going to divide every mole value through by oxygen's mole amount. And why am I doing that? To make sure that I'm getting a number that is at least 1 or higher. So anything divided by itself is 1. Taking the 6.64 moles of hydrogen and dividing by 1.332 moles of oxygen, doing that calculation, I see here that I'm getting a number that is very, very close. I'm looking for whole numbers at this point, or something very close to it, and I see that I've got a number that's very, very close to 5. It was 4.98 on my calculator, but I see that that's very close to the whole number 5. Doing the last calculation with carbon, dividing carbon through by moles of carbon through by 1.332. And what is my calculator showing here? I see that I do not have a whole number, right? So that was the goal, to get this whole number ratio, but I still don't have a whole number. In fact, what I have, and let's give it to 3 significant figures, is 4.50. So, I was hoping to have a whole number ratio. I still don't, but I see what I can do here to create it. And that's where this last step comes in. If you do not have whole number ratio. Multiply all of the values through by a number to get a whole number. And you're saying, what does that mean? If I look at the decimal 0.5, I know that 0.5 correlates to the fraction 1/2. So if I multiplied 4.50 through by 2, I would get a whole number, and that whole number would be 9. But what you do to one substance, you have to do to all of the others. So I'm doing the same calculation so that I keep the ratio consistent throughout the compound, multiplying everything through by 2 to come up with these whole numbers. So I now know that the empirical formula of the compound, therefore the empirical formula equals C9H10O2. I have calculated the empirical formula of benzyl acetate. So we have done the first step. But we were asked to calculate the molecular formula of benzyl acetate as well. That means I'm going to have to come up with what the value of N is, because you take the empirical formula and multiply it through by N, which is always a whole number, in order to get the molecular formula. And right here is the equation that tells you how to find N. Take the molar mass and divide it by the empirical formula mass. Molar mass, well, we would need to know that molar mass, and we do. It was stated in the problem. The molar mass of benzyl acetate is 150.2 grams per mole. So carving out a little space here. N is going to equal 150.2 grams per mole. That is my molar mass. And now I have to divide it by the empirical formula mass. So that means I have to take my empirical formula and add up the masses of 9 carbon, 10 hydrogen, and 2 oxygen. So 9 carbon, 10 hydrogen, and 2 oxygen. And when I do that, I get, lo and behold, 150.2 grams per mole. What that means is that the value of N is 1. And I need to state here, it must be a whole number. Whenever you do this calculation, you must get a whole number. If you don't get a whole number, that indicates there's an error somewhere. Either your empirical formula calculation is incorrect and you have the wrong empirical formula, or you did not add up the empirical formula mass correctly, or the molar mass was not correct. Somewhere there's an error in the problem. N must be a whole number, and it is in this case. So what does that mean? That means that the molecular formula equals the empirical formula multiplied through by 1. Well, anything multiplied through by 1 is itself, and the molecular formula for benzyl acetate is also C9H10O2. In other words, the empirical and the molecular formulas are identical in this situation, just as we saw in the example with water.